Sample problem 15.14. The Haber process, which is used industrially to generate ammonia, largely for the production of fertilizers, is represented by the equation N2 gas plus 3H2 gas to form 2NH3 gas. Using data from Appendix 2, determine the delta H of reaction under standard conditions for the process and indicate what direction the equilibrium will shift if the temperature is increased. What direction will it shift if the temperature is decreased? So for this one, it says to go to Appendix 2. So you may or may not remember this from Chem 11. If you have an equation we can tabulate heats of formation to calculate delta H of reaction under standard conditions, or even non-standard conditions if we have the correct table. And the way we do that is we look up their standard heat of formations. And the units of that are kilojoules per mole typically. And they're often at 298 Kelvin, at least in general chemistry textbooks they are. So you go back to Appendix 2 and you look those values up. N2 is an element, so it's 0. H2, its standard state is H2. Hydrogen standard state at 298 Kelvin is a gas, so it's also 0. And then NH3 is minus 46.1 kilojoules per mole. Okay, so then use this equation. Delta H of reaction is equal to the sum of the number of moles of a particular product times its heat of formation under standard conditions, as for the products, minus the sum of the number of moles of a given reactant times the heat of formation of that reactant under standard conditions. So for this particular equation, they picked one that's pretty simple because two of them are 0. So that means that you would find that delta H of reaction would be the number of moles of the product is 2. So 2 times the heat of formation, which is minus 46.1, minus the sum of the reactants. Now there's 1 mole of nitrogen and 3 moles of hydrogen, but both of them are 0, right? Both have heat of formations of 0, so it's minus 0, minus 0. So you just get minus 92.2 kilojoules per mole. Now, they ask you to do that question really just to figure out whether this reaction is endothermic or exothermic. If you watch the discussion of this section, what I did was I talked a little bit about how we analyze the shift in temperature and how that affects the equilibrium for these types of reactions. And here's the way you go about it, the analysis. We just did all that just to figure out that it's exothermic. The point is that if it's exothermic, what you do is you write the equation again. I'm going to write it again just because I want to show you where to write the delta H. If it's exothermic, you put it on the right side as a product. If it were endothermic, you would write it on the left side as a reactant. Okay? But since this one is negative, that means it's exothermic. Positive. So let me make a little table here. If it's positive, that's endothermic. And you write it as a reactant. If it's negative, that means it's exothermic. You write it as a product. Okay. Now, if the temperature goes up, that's another way of saying that the heat goes up, so delta H goes up. If the temperature goes down, if it's decreased, that means delta H is going down. Okay? So here's how we do. Let's go back to the question. Indicate what direction the equilibrium will shift if the temperature is increased. What direction will it shift if the temperature is decreased? Okay, so delta H is on this side. So if the temperature goes up, delta H goes up. Delta H is a product. So if you increase the amount of a product, that will shift it that way. Okay, think of it this way. Q would be greater than K because we'd have more products than we originally had. And so it would shift that way. So the answer then is if the temperature is increased, the reaction shifts to the left. And then on the other hand, if we decrease the temperature, that means we're decreasing the amount of heat, then the reaction will move in that direction. So if the temperature is decreased, that means the reaction shifts to the right. Okay? There you go. And it would be reversed if delta H were positive. If delta H were positive, you would put the delta H on the reactant side and everything would be the opposite. Okay? There you go.